Okay, so welcome back, everyone. So we are going to be starting chapter 5 today. This material, as you know, will not be on Friday's exam, just as it says in the syllabus. This material is an exam number 2. I like leaving that slop day, like I said, just in case something happens and we need to miss a class, then at least we don't have to move the exam. Good. So that being said, I know the exam and exactly how it's going to be administered and exactly what's going to happen is on everyone's mind, and trust me, it's on my mind as well. I'm planning to write you guys at least one more email. It might be tomorrow, but you know, sometime long before you have to take the exam. Might be tonight, might be tomorrow. I kind of want to wait as late as I can so that I have as much information to give you as I possibly can. But you guys in 505 in this section will have an advantage over 504 in that at least I'll have been through the scheme once with them, because I've never done this before, giving an exam in person and online at the same time. But for those of you taking it online, I'm going to say it on faith that at high noon, the exam will become available on eCampus and you'll be able to download it. We are not going to use a lockdown browser. I've heard nothing but bad things about the lockdown browser, that it doesn't even work as intended in any way. It crashes after a while, so completely charming. No, you'll just use your regular browser to get that done. But you'll download the exam from eCampus. It'll be an equivalent exam to the ones that people are taking in person. And we'll ask, there will be a Zoom meeting. Probably it will be the same number, though if it's not, obviously I'll let you know. The only difference is, if possible, I'm going to add a level of security. You might have to log in with your UIN or something like that, or I might give you a password. I'm still waiting for direction on that from some of my colleagues. Happily, Dr. Pennington just did this, actually. He just finished doing this. So I'm going to be hitting him up for some information for what he did. So at least I will have some guidance and all that by the time this thing actually happens. And then I usually give a little more than 50 minutes, maybe 55 minutes or something like that. I will have to ask those of you taking it in person to understand that I do have to give a bit of extra time to the people in taking it online, because they have to photograph or scan their work in and convert it all into a PDF or whatever technology they may happen to use. So that does take a little bit of time. And so one thing I know I'm going to say in the eventual email is, those of you taking it online, please do not plan on working for that extra time. I'm not going to take responsibility if you miss the deadline because you were working till the very end. But it's the sort of thing, as I recall from last term, it may take several tries for you to be, to get it submitted and be absolutely certain that it's been submitted on eCampus. There's still a bunch of stuff I don't know. I do not know if I'm getting graders. I hope to find that out today. And I hope to find out today that I will have graders, or it's going to be a bad scene because there's 250 of you or so all told in both sections. I believe that I was promised some graders, so we will see. Yep, for those of us who don't have a printer, have to write out the questions at home. Do you have to write out the whole questions, or can we just number them? No, you don't have to write out the entire question. And I'll put that in the email too, I think. But in case I forget, since goodness knows it's possible. One thing I am going to ask those of you who write out your answers is that you put all of your answers for one page on one page, and then change pages even if there's a lot of space left, and put your answers for the next page on the next page, etc. That reminds me of another thing. For the proctoring, since this will be proctored and it will be recorded, I want those of you taking it in person to know that too. We're going to be putting precautions in place. So those of you taking it online, we're going to expect that you have either your cell phone camera or maybe your laptop camera on you and your workspace the entire time. And that will be recorded, and I will check later if I see anything that looks suspicious based on what I see on the exam. So, that will all be available for me to do that later. Of course, you're going to have to take your camera off of you in order to photograph your exam pages if that's what you're doing, if you don't have a scanner. So obviously that will be fine. Now, the exam multiple choice, the exam is not multiple choice. It will be reminiscent in format of the old exam that I put on eCampus. I don't promise your exam will be identical in length and format, but it will be taken during class time, yes. So now I understand stuff's gonna happen. I'm going to be putting out constant small fires on Friday because things are gonna happen. My goal is that everyone who intends to take the exam and not to get a 0, my goal is gonna be that everyone gets to take it in the end who falls into that category. And I understand there's gonna be some, you know, some exploits that I have to go through in order to get that to happen. But yes. Well, what, sorry? No, no, because I'll be watching you. And anyway, I think there's cameras on in here too. It's all become a little bit dystopic, hasn't it, with all the cameras on us all the time. But yes, but yeah, I know, one way or the other. But yes, so, but understand I am going to be proctoring all of you in person and all the people online at the same time. So I've already learned how to turn off the screen so that you can't see what's going on there. Because I want to be able to have my email open in case there's, you know, problems, but, and we're gonna have to expect that there will be problems, especially this first time. We'll deal with them. I'll make sure that everyone gets to take the exam. How much time will we be given for printing and scanning? I haven't decided an exact time, but probably something like 10 or 15 minutes. That's certainly at least 10 minutes. But like I said, and that will be built in. You'll see how much time you have to take the exam when it becomes available. You'll see what your deadline is. And what? And yes, you'll see what the deadline is. So, oh yeah, and that will include the time for printing and scanning. So, like I said, I will not take responsibility if you miss the deadline due to using too much time to work. So please, especially with everyone doing it at once, my expectation is it will not be quite as bad as last year, because from what I can tell, the majority of you are planning on taking it in person. But at least that's what it seems like so far. That could always change. But there were issues last year if, you know, 100 people were bombarding the internet with trying to turn it in all at the same time. I don't think it'll be 100. I think it'll be more like 30 or something like that. But still, be sure that you use that time. It may take you several tries to get it converted to PDF and uploaded. So please do leave that time in order to do that, because I will not take responsibility for otherwise. A couple other things that come to mind. A couple of you have asked me if you could download the exam onto some sort of tablet or other device, like an iPad or something, and just draw on and take it on the device. Some people did that last year, and it worked. That's fine with me, as long as you can get it converted into a PDF and submitted by the deadline, then we're fine. What else am I forgetting? I know I'm forgetting stuff, but like I said, you'll have, I'll try to get at least one email out to you before, you know, at least say by tomorrow night or something like that, you know, in plenty of time for you guys to take the exam. I really do hope I have graders. I always intend for the exams to be graded within a week, so you don't need to ask when you'll know your grades. My answer is hopefully within a week. I am going to ask that you understand, though, that one policy that I have is I will not discuss individual exam grades or exam performance until everything's graded and we know all the data, we know what the average is, and believe me, at the very second that I know those results, you'll get them. They will appear on eCampus in the gradebook. As soon as I know what everyone's grade is, what the average is, what the curve is, if any, I will tell you that also in the header on eCampus. So you'll see that when you look at the column. The very second I know, I will upload that data. And I'll try to keep you apprised in the intermediate classes too as to how grading's going. Have my graders showed up? Please, I hope I have graders. This is going to be a mess if I don't, but let's hope for the best. But yes, my policy is I will not discuss individual exam results until all the exams are graded. I know what all the data looks like. I know what the average is. And even once you've gotten it back and gone over it with the answer key. And so I will eventually post all of that. I'll post an answer key, assuming we actually get all these graded before I die. Oh, sorry. If I didn't laugh, I'd cry sometimes. But yeah, but before that, I have no comment on the exam. I cannot discuss how an individual thought they might have done or anything like that. So I'm going to ask you to understand that. But we'll get them done one way or the other just as quickly as possible. And we'll see. We'll see how it goes. I don't know exactly what's going to happen. One thing that I think I'm going to ask of those of you taking it in person is if as many of you as possible could either wait outside or at least kind of stay in the back of this room. I'm still a little unclear. I may need to use the entire round after all, since again, so far it looks to me like more people are taking it in person than I expected, which is all fine. So like I said, check your email. I will be emailing you at least once more, by tomorrow night at the latest, if I have any other information besides this. But luckily for you guys in 505, at least I'll have kind of been through it all once. So I'll know the good, the bad, and the ugly. Good. So today, as I said, we're starting chapter 5. And the idea in chapter 5 is this. We have one more structural issue that we have to deal with, or issue in terms of structure, that we have to deal with before we can get into the real organic chemistry, so to speak. The reactions, the mechanisms, all that stuff that you've been told to expect to get in this class. And that issue is the issue of chirality, the idea that you can have stereoisomers that don't involve alkenes, like cis and trans alkenes, which we'll get to eventually, and also don't involve cis and trans in cycloalkanes. No, there's another issue that you can have even with a molecule with a single carbon atom, by which stereochemistry can arise. And that's this issue of chirality, of stereochemistry at tetrahedral carbons, or tetrahedral centers in general. So I've put up here some definitions. I believe I put them all in the class notes too, but I just wanted to make sure that we had these words defined so that at least I could use them. But is there going to be a section within the exam that will tell us to submit our exam on eCampus for online? Well, there's going to be like there's like a section or column on eCampus at which you'll submit your work. I think it uses Turnitin or something like that. But yeah, that's what everyone did last year. They just submitted it on eCampus. So, but I'll have to leave the timing to you guys. Good. So maybe before I even get into defining these words, I just want to bring up the idea itself, which I bet most, if not all of you have noticed, which is you can take even a simple molecule like 2-bromopentane, but the issue is that there isn't just one 2-bromopentane. There's two of them, right? And this structure is not wrong, and it's fine if you're not trying, if for your immediate purposes, whatever question you're answering, you have no intention of showing stereochemistry, and maybe you don't have to. Owl will often say that. Don't worry about stereochemistry. In that case, a structure like that is fine. But going beyond that, there's actually two different 2-bromopentanes. One of them is like this, and one of them has the hydrogen in front and the bromine in back. Actually, let me redo this. I'm just being picky here. I want them to match. So one of them has the bromine in front and the hydrogen in back, like that, and the other one is the opposite. And those two are different compounds. They are not, you can't interconvert them. They are permanently different from one another. So this is a kind of stereoisomerism that you can get without any double bonds and without even any rings, though this certainly can occur on cyclic compounds as well. And this is something that arrives whenever you have a chiral carbon atom, which we define as a carbon atom. It's usually carbon. Other atoms can be chiral also. I very much doubt we'll run into examples like that, although they're not that scary. One that will seem quite obvious when you think about it for a moment is if this can happen with a carbon atom, surely it can happen with a silicon atom, right? And silicon's right below carbon in the periodic table. I just don't know how many silicon compounds we're going to be dealing with the next 2 semesters. But largely usually these will be carbon atoms. And the phenomenon arises when you have an sp3 hybridized carbon like this one that has 4 different groups attached, meaning that when you list the things that are directly attached, they're all different. H, bromine, methyl, propyl. See what I mean by they're all different? As soon as that happens, then you've got yourself a chiral carbon and the possibility of chirality in general. And so what that means for us is since these 2 compounds are different from one another, I'm sort of giving you a heads up into where we're going to get to by the time we end the class. I don't think we're going to start the Conning-Gold-Prelog system today, but I would at least like to get us that far, and that's where we'll continue on Monday. And the issue is this: if these 2 compounds are different, then we can't just call them both 2-bromopentane. We need some other way of distinguishing those 2. And that's the so-called RS or Conning-Gold-Prelog system. And we'll get to that starting on Monday. But I just wanted to show that, this sort of thing has probably come up already. Now, do you have to draw the wedges and dots? Again, it depends what you're being asked to do, what you're trying to communicate. There are times when you can just draw, when you're not really, when there's no reason for you to have to show stereochemistry. And in that case, you can just draw a straight line, that's fine. Other times, we will need to be specific about stereochemistry and note that there's 2 possibilities that are different from one another. So the way you know what you have to do is by reading what the question or task at hand is telling you to do. But this is what we mean by a chiral carbon atom. It's one that is sp3 hybridized and bonded to 4 different groups. So if it's not sp3 hybridized, game over. The carbon is not chiral. It has to be sp3 hybridized. And if any 2 of the 4 groups directly attached to it are the same, game over. It's not chiral. Another way of thinking about it is as soon as there is a plane of symmetry in the molecule, it's not chiral. For example, one thing you might have noticed is a molecule, simple molecule like maybe methyl cyclohexane. Well, this molecule is not chiral. That's why you don't even have to bother with wedges and dots here, because the compound with a wedge methyl group is the same as the compound with the dot methyl group, right? There's a plane of symmetry that runs down the middle of the molecule. That's just another way of saying that 2 of the 4 groups attached to that carbon, sure, we've got methyl, we've got hydrogen, and then we've got this group, but we've also got that group, which is the same, because there's a plane of symmetry. So saying that a molecule is a plane of symmetry and saying that 2 of the 4 groups are the same, it's just different ways of saying the same thing. So you do need to know what a plane of symmetry is in order to understand this material. But I'm talking about imagining a mirror plane running right down the middle of the molecule. Can you all see what I mean, that the left half and the right half are the same? Right, so that molecule is not chiral. Now, as soon as I do this, though, as soon as I do this, game on. And that structure is still fine. It's just not showing any stereochemistry. Will it lose points? Yes, if the question asks you to show stereochemistry. No, if it doesn't. And then we would have to show whether we mean the one with a wedge methyl or a dot methyl. And you can also show the hydrogens. You don't have to. Like I did over here. You can show the hydrogen too, but even if you don't, it's understood. So, right, we've already been through that. Yes? Ah, great question. The question is about 3-bromopentane. Well, this molecule, you can think of it as having a plane of symmetry. That would be true. But also this carbon has 2 ethyl groups on it. Game over, not chiral. But if you do this, now game back on. Yep. So these are some examples of where you will or will not see chirality. But as soon as any given sp3 hybridized carbon has 2 of the same group on it, or as soon as there's a plane of symmetry, which is, it's just 2 different ways of saying the same thing, as soon as either of those phenomena occurs, game over. It's not chiral. And that's now chiral atoms. A molecule as a whole can also be chiral. And by the way, here we go again. You know how we organic chemists are. We're never happy unless there's at least 2 terms that mean exactly the same thing. We also call chiral molecules optically active molecules. And there's historical reasons for that. I'll go into that a little bit. I don't really consider this class to be a historical survey, but I'll go into that a little bit. That being said, optically active is kind of the old term. People nowadays more say chiral. If you say optically active, you'll sound like you're back in the 70s or something like that. So it's not wrong, though. It will be completely understood. But a chiral molecule is going to be so by virtue of its having at least 1 chiral carbon atom in it, generally. But a chiral molecule is also non-superimposable on its mirror image. In other words, there's no plane of symmetry. And I'll show you what I mean. I have some models ready to show you on our document viewer. As long as, God willing, and the creek don't rise, that all works. Those of you in class can see my little models. You may be wondering, how do I do this normally under normal circumstances? Well, I have these, I inherited from my predecessor. He actually made these Tinker toys with like big Nerf balls. And so, you know, I would use those normally. That being said, in a classroom this size, I don't think those would be terribly effective. So that's why I'm deciding to go with these molecular models. Can 2 chiral atoms cancel each other out and make the molecule non-chiral? Excellent question. Answer is yes. And you're not even in Monday, you're in Wednesday now. So we'll get there. Another way of thinking about it is with the idea of a racemic mixture, which we'll also get to. But welcome to meso compounds. That's way ahead. That's next week. That's Wednesday. We'll get there, little by little, 1 step at a time. Good, so we've defined chiral molecules, so a molecule as a whole can be chiral. I'll just finish defining the terms before we get into the issue of why should we care about this, which is always a fair question. Right, so what do we mean by enantiomers? Well, enantiomers are 2 molecules that have this property and are mirror images of one another, like these 2 over here. Or up and down methyl group over here, or up and down bromine over here, right? These are molecules that are non-superimposable, meaning that if you made models of these guys and tried to bend them around, I have a somewhat different molecule up here, but I'll demonstrate that shortly. There's no way you can make every atom on this molecule fall onto the exact same atom of this one. Always something's not going to match up. And so molecules that are like that, that are mirror images and are non-superimposable, we call those enantiomers. Yes? No, superimposable means immediate, just like you can't superimpose your left hand on your right hand, right? It's not going to match up. Right, yeah. And actually, that's actually not a bad way of thinking about chiral molecules. They are molecules with handedness. And there will be 1 left-handed one and 1 right-handed one. And those are what we mean by the 2 enantiomers. So yeah, that's absolutely not a wrong way to think about it, especially when you consider, when you start to think about what the implications of this might be. When you think about, and I am no biologist, so I'll probably murder this, but even I have some vague understanding that pharmaceuticals, drug molecules of a certain shape, that then will fit into some receptors on cell membranes. Am I close? And those receptors in turn have the right shape. And if the molecule doesn't fit, then it doesn't interact. And so that's going to be an issue even with 2 enantiomers. So one of those will be the right fit and one of those will fit and the other one won't. And you could say the same thing about enzymes and substrates, same idea. But be that as it may, so we call two such molecules enantiomers. And the word enantiomer implies a relationship between two molecules. It's not proper to say this molecule over here is an enantiomer, because the implied question is of what? You know, there's no molecule standing alone that is an enantiomer. It's always two of them. There's two molecules that are enantiomers. Good, and last but not least, since it's a somewhat useful term that we'll need sometimes, we have a special word for a 50-50 mixture of enantiomers. In other words, exactly the same amount of the left-handed molecule and the right-handed molecule. We call that a racemic mixture. Can you have a mixture that's not 50-50? Absolutely you can, but that's not a racemic mixture. And so that will have different properties than a racemic mixture. So those, I think, are all the terms I'm going to need for now. Maybe I'll move to my little document camera, if I can manage it. Yay! Oh, it's so nice when technology works. Good, so here's an example of two enantiomers. This molecule, you can think of this as a carbon with a hydrogen, a chlorine, let's say an iodine, and a methyl group. So how are we going to name that thing? Well, I guess it would be 1-chloro, 1-iodoethane. How about that? Something like that. Except, again, those are both 1-chloro, 1-iodoethane. So we're going to need a way to distinguish them in their names as well. And getting to your question about superimposable, there is no way that you can make this molecule, you can turn it in any way so that everything matches. You know, let's say I managed to make the iodine and chlorine and carbon match. I can't really make them take up each other's space, but I think you can see those are overlapping. Well, but then essentially the hydrogen and methyl are in the wrong places. See, this methyl's back here and this one's back here. Or if you tried to make, let's say, the methyl and the iodine, should be possible. It's always possible to match up two. Yep. But now look, now the hydrogen and chlorine don't match. So there's no way to exactly superimpose these things. That's what we mean when we say they are non-superimposable. Non-superimposable mirror images. The non-superimposable part means that they won't match up like that. That they are mirror images, I think, is pretty evident. You can imagine a mirror plane slicing right down the middle here. And so that's the phenomenon of chirality and of stereoisomers, particularly of two molecules that are enantiomers. And what you would find if you had, say, two chlorines or two iodines or two methyls on that carbon is then the two mirror images would be superimposable, right? Because the compound is no longer chiral and that carbon atom is no longer chiral. So as soon as any carbon atom is either not sp3 hybridized or has any two groups that are the same, game over. It's not chiral. Now I'm getting questions in chat. Did he say the Zoom link for the exam is going to be the same as the class one, or are we going to be sent a new link before the exam? I think it's going to be the first thing, but if the Zoom link or Zoom number changes, then I would at least send you the Zoom number. You don't even need a link, actually. You can just enter the number. But if there's a different number, then I will of course let you know about it. But from what I'm hearing so far, I think it will be the same number. The only difference is we'll need to up the security. So it might be that you'll need a password, which of course I will give you. It might be that we'll have you sign in with your UIN, something like that. But to be determined, I'm afraid. We're going to have to think on our feet. Okay, so there's an example of a chiral molecule, and it's two enantiomers. So again, that's the issue that we're going to have to tackle ultimately, is that we need a way of distinguishing those in their name because they are different molecules. It's not enough to say 1-iodo, 1-chloroethane. Okay, and I think that's all I really need about that. Oh, I'm leaving out the biggest, hugest elephant in the room, which is who cares? Can you explain the difference between superimposable and non-please? Superimposable means that you can put the two things right on top of each other and everything matches. So my left hand and my right hand are not superimposable. This doesn't count, you know. If we're thinking, because you're not, you know, that doesn't count. Non-superimposable means that no matter how, well, it means what I demonstrated before, and I'll do it again, with that molecule. It means that no matter how you turn the two molecules, you can't make both carbons fall onto each other, the chlorine fall in the chlorine, the iodine and the iodine, and this hydrogen and the hydrogen. It's not possible, and if you play with models a little while, I think you'll be able to convince yourselves of that. And you can always make two match, like here, oh, whoops, I didn't do that right. Or I'm suddenly blind, something like that. That does happen. Okay, there we go. Like here, I can make the two carbons go together. Can you see how the two carbons are superimposing? I mean, except I can't make them occupy each other's space. But if I could slide them right into each other. Does that help? Is that kind of what you meant? Yeah, and so those three atoms are superimposable, but the others are all wrong. The methyl group and the chlorine are wrong. And I mean, you can convince yourself of that if you play with models, but I promise you won't succeed. They are mirror images of one another and are permanently non-superimposable. But definitely get with some models. That will, I think, help. Good. Where was I? Oh, I was about to get to the question of who cares, which is something you can always ask. So who cares about all this? Why are we bothering? And the answer is, well, I think, oh, question? Does every atom what? Every atom has to match up with the exact same one if it's to be superimposable. That's the definition of superimposable, if you will. Every atom matches up with the exact same one in the other. In other words, the molecules are identical. Right, and there'll be two other things elsewhere that aren't matching up. That's always going to be the case with chiral carbon atoms, no exceptions. You will not find an example of a chiral carbon in which they're superimposable. It's not possible. There are no exceptions. So the question again was about things being superimposable and when they are and when they aren't. Good, so is there a difference in reactivity between the enantiomers? Maybe. We'll ultimately get to that. Sometimes yes, sometimes not. Certainly there's going to be a difference, which actually, I did not plant this question, I swear. Actually, that's a good lead into what we're talking about here. One way in which enantiomers may differ in reactivity is in biological systems. If you're talking about whether something will fit into a receptor on a cell membrane, let's say, then one enantiomer will and the other one will not. If you're talking about whether something will fit into the active site of an enzyme, one enantiomer will, the other will not. And I think you can see this has pretty drastic and pretty important results. This whole issue of chirality in drug molecules, I would say, at least as far as I've been able to ascertain, I would say people didn't fully appreciate the issue until sometime around the middle of the last century. And that's because a lot of the molecules that were in drugs, like you might be familiar with a minor importance drug called aspirin, you know, put out by a little company called Bayer that had some minor success with that. Well, draw the structure of aspirin. It's not chiral. It's acetyl salicylic acid. Whoops, CH3. CO2H, carboxylic acid group. There's no chiral carbon atoms. Everything's either sp2 hybridized, all of these are sp2 hybridized, and the methyl group, of course, is not chiral. So there's no issue here. But around, I think it really started to take off in about the late 50s, early 60s. So even I wasn't around then. but you might have heard that around that time, a drug came out called thalidomide that was for morning sickness. And pregnant women were taking this, and it did indeed relieve morning sickness. But what they didn't fully appreciate was that in the way they administered the medication, they were giving the patients the racemic mixture. So it had both enantiomers. One of them was the good actor. That was the one that relieved morning sickness. The other one, however, caused horrible birth defects in the babies. And you've probably heard about this. It was really, as you can imagine, a big deal. These thalidomide babies, very sad. But you know, and they realized that that was the reason. And we have somewhat less dramatic examples of this now, even nowadays in terms of over-the-counter medications. If you consider Advil, you know, or ibuprofen, that's your Advil, your Motrin, all these types of drugs. If you look up the structure, it's easy to find with a Google search, you'll be able to convince yourself that molecule is chiral. I think it is one chiral carbon atom. And so that exists as two enantiomers also. This also leads to the question of, is the problem bad enough that we have to even separate the enantiomers one from another? Which, by the way, is exceedingly difficult. And another way to pronounce that is exceedingly expensive. It's possible, but very, very costly. And obviously with something like thalidomide, you would need to do that and be sure you're providing the patients only the good enantiomer and none of the bad enantiomer. And there are ones like that, but are maybe somewhat less dramatic than that. I mentioned Advil. I could be wrong about this, but I think they actually give the racemic mixture. The deal with Advil is I think the good enantiomer, good quotes, good enantiomer, is just a little toxic to the liver. The other one is kind of pretty toxic to the liver. So that's why they say you shouldn't take too much Advil. It becomes too much of a strain on the liver. And anyway, I think once it hits your stomach, it racemizes and turns one enantiomer into the other anyway. That's why I think they don't bother. I see a question in chat, just let me give another example. Some drugs, they actually provide both enantiomers and it's fine. There's a psych drug, I'm forgetting what it's called, but actually they do both. You can get it as just the one enantiomer or the racemic mixture, and both are fine. I think the activity is pretty much the same. Obviously, the pure enantiomer will be more expensive. Does chirality only occur with sp3 atoms? Yes. Yeah, we do require that individual atoms, in order to be chiral, must be sp3 hybridized. Anything sp2 or sp, game over, not chiral. No, that's fine, worth saying. Sort of implied in the question is, has there been anyone evil and creative enough to actually come up with a molecule that, in spite of having no sp3 hybridized carbon atoms, is still chiral? And the answer is yes, molecules like that exist. I don't think we'll ever see them, but you can look into that if you want. They are able to make like spiral-shaped molecules that can have right-handed or left-handed spirals, sort of, and that's usually how it's done, helicenes and the like. But I don't think we're going to run into those. But certainly for individual atoms, that's clear. They must be sp3 hybridized to have any hope of being chiral. Good, so I think I've explained the importance of all this. Let me see, I have 10 minutes left. One last issue that I want to get into before we do our reef session is just this whole business of optical activity. Why is a chiral molecule called optically active? And you can use that term, it's absolutely correct. And that goes back to the history of all this and Pasteur's groundbreaking work, in which, if I'm not wrong, he had to use a microscope and painstakingly with tiny tweezers separate left-handed crystals from right-handed crystals. Absolutely insane stuff. You know, this is not a science of history class, nor is it an experimental methods class. I really don't care if you can draw me gorgeous pictures of polarimeters or anything like that. But I at least wanted to talk about that a little bit so you knew where all this came from. Is that you can measure you can measure which of two enantiomers you're dealing with and what the two properties are. You see, the problem is this. Enantiomers have identical physical properties except for one. And there's only one by which you can do an experiment and distinguish them. That's not true, by the way, for cis-trans stereoisomers. They have different physical properties. Same thing with cis-trans stereoisomers, that is with either alkenes or cycloalkanes. Those can be distinguished pretty easily, and thus they can be separated pretty easily, which is pretty important. But not so for enantiomers. They have identical physical properties, same solubility, same melting point, same boiling point. You can go all the way down the road. All of those are identical. Next term, when we learn about spectroscopy of any kind, enantiomers will have identical spectral data. The only way you can distinguish them is by doing what's known as a polarimetry experiment. And that involves making a solution of a certain, oh, it's cutting out? Are we okay then? Well, let me know. But anyway, you need to make a solution of a certain concentration. Of course, I don't care if you memorize all the particulars. You need to put that in a cuvette of a certain length. I think it needs to be 10 decimeters that we now shine plain polarized sodium D light through. So that's of a particular wavelength. It's a pretty unmistakable orange yellow color. And what happens is if the material in the cuvette is chiral, it will now rotate the plane of propagation of plain polarized light. I got corrected on this many years ago at my other school by a kind physics major because I had been saying it's an easy mistake to make. But so understand that it's not that the beam of light bends, but it's just the direction of the plane of polarization rotates one way or the other. And it will rotate counterclockwise for one enantiomer and clockwise for the other. That's basically how it will work. And so the two optical rotations, as they're known, for two enantiomers will be equal in size and but opposite in sign. So one might be minus 37.6 degrees and the other one would be plus 37.6 degrees. Of course, you don't need to memorize any of this stuff. I'm not getting into the numbers so much here. But that was really the only way they could distinguish it. One last little interesting thing, now that I've actually mentioned racemic mixtures, this also gets back to, it sort of gets back to another question someone asked in chat. What if you put a racemic mixture into the polarimeter? Well, as you might guess, the optical rotation will be 0. They will cancel each other out. But otherwise, you will have your plus enantiomer and your minus enantiomer. So, and that's all fine, but the trouble is we can't know whether a particular compound, just by looking at its structure, is the plus or minus enantiomer without doing an experiment. That's kind of not very good. We need a way to figure out which enantiomer we're looking at and give it an absolute configuration just by looking at its structure. Welcome to the Conning-Gold-Prelog system, or the RNS system. So I don't think, I mean, I've got like, 7 minutes left. So I don't think we're going to be able to go there specifically today, but that's where we're going to start on Monday. And I at least wanted to get that far to show you the importance of it all. Because you're not going to be provided with a polarimeter under your seat for the second exam. We need a way to know which one we're talking about just by examining the structure. So that's Monday. Okay, with that, any questions before I was going to go on to the reef session? Yes. Well, the question is, I think you're kind of asking if there can be multiple stereoisomers, like there's multiple chiral carbons and maybe different possibilities. Is that kind of what you mean? No. Well, oh, I see what you mean. Is there more than one way in which it can be mirror images? Sure. I mean, you can even do that with this molecule. We could turn this one like this and this one like that. But there's still going to be two enantiomers. And pretty much, however you line it up, they're going to be mirror images, and those mirror images are not going to be superimposable. Is that kind of what you meant? Now, the more complicated question, I don't know that we're going to get to before Wednesday, which is what happens when there's multiple chiral carbons. Now, how do you deal with it? But we'll get there, all in good time. Good. Looks like we're good in chat. Let me start up our brief session. Like I said, I just have one question for you today. I think it's timely, given, you know, that, oops. I think it'll be good practice for the exam. So basically, and I'll start this in a moment. Basically, oh, no, don't do that. Don't do that. Sort of shove chat over here. Sorry, guys. So I'm giving you substituted cyclohexane here. One of these 5, and I've labeled them here A, B, right, C, D, E. So I've labeled them all. Which of those is the one you'd get after you do a ring flip conformational change like unto the way we did it in class? So I'll start this up. Let me get my phone so at least I have a clock. Actually, there was one thing I thought I still needed to do, but thanks to questions some of you were asking, we already covered that. So we're good. Yes. Yeah, I labeled all of them. If you look just below the chair, you'll see a letter there, A, B, C, D, E. Yep. So that being said, I think we're going to largely end class with this. So I'll give you like 3 minutes all told on this. So we'll go about 1 more minute. One other thing that occurs to me that I don't think I've mentioned yet, those of you that are taking the exam in person, since I'm not going to be able to project the screen, since I might be answering emails and things like this, you may use your cell phone as a clock. So that will be fine on Friday. I'll still try to announce there's this many minutes left, that many minutes, you know, but that will be totally fine if you do that. But I will be keeping my, I'll have to have eyes in the front of my head, the back of my head, elbows, you know, whatever, to keep an eye on you guys and on in chat just in case everything works. Just in case anything doesn't work, I should say. Let's say another 20 seconds or so. All right, last chance, going. Looks like that's about it. Okay, so, well, unless I've completely lost my mind, which is always an open question, you just want to pick up any 2 opposite carbon atoms. I find it easier to see if with the chair in this shape, I pull this one up that way and this one down that way. So in so doing, all of the other 4 carbons in the cyclohexane ring will all turn themselves inside out. Everything axial will become equatorial, everything equatorial will become axial. And this carbon will appear to move up here, this one will appear to move down there, so everything's gonna kind of look like it goes clockwise. And if I'm not wrong, what you get is B. So the chlorine starts out up and ends up. The chlorine starts out equatorial and ends up axial. But I think that's the best answer. That one is the corresponding ring flip interconversion structure for this one. Likewise, this isopropyl group starts out pointing down, but also equatorial. It winds up still down. That stays the same, but now it's axial. Obviously, that would be significantly higher in energy than this one. So that one's the lower energy conformation one by far. So I think B is the best answer. I'll set that up in the grading in just a second. And by the way, if any of you who were bored and wanted to name this thing, what about trans 1-chloro-4-isopropyl cyclohexane? That's what I think it is. It's harder to see with them both being equatorial that this is in fact trans. It's easier to see when they're axial, but they're both trans. So I think the best answer is B. That was certainly the one that most people put. Good, and I think with that I'm actually out of time. So we'll end there, and I hope everything goes smoothly for us on Friday, but I will be communicating with you at least once before the exam. So other than that, have a great day.